Sure.
Good morning, and thanks, Jonah, for that introduction. And thank you to everybody for joining. Jonah, I think I need permission to share my screen.
You're right.
Okay, I got it now.
Yeah, sorry for that.
Right, so thanks everybody for joining. My name is Aditya, as Jonah just mentioned, and I come from this institute called International Center for Theoretical Sciences in India. I'm also a part of the LIGO Virgo Kagra collaboration and also the LIGO India scientific collaboration. And today I'm going to be telling you about how we estimate source parameters from gravitational wave signals. Okay, so what is indeed the problem of source parameter estimation? The problem is to go from these wiggles in our detector that we see, and you've probably heard about this quite some bit in the last 2 days. How do we go from these wiggles that we see in our detector to the measurement of parameters of the signal, say the mass of the black holes in a binary black hole signal? Right? But you would ask, why do we care about estimating parameters? I think most of the answers were given by Maya's talk yesterday. But one of the things is that it's not just enough to detect gravitational wave signals. We want to understand the physics and astrophysics behind these signals. For instance, we want to understand, say, what's the equation of state of neutron stars that yesterday was mentioned as well. We want to, say, perform tests of general relativity. We want to see how well these signals agree with predictions from Einstein's theory of general relativity, and for much more interesting and impactful science. All these problems actually involve parameter estimation in a very, very fundamental way. Okay, so just to give you an overview of what's to come in the slides, what are the tools that we use to actually estimate parameters from the data? So the first thing that we need is models for both the signal and the noise, and we'll talk about that a bit in the next few slides. We need this really, this theorem that maybe most of you had studied in your high school. For instance, it is called the Bayes theorem, and this deals with conditional probabilities. Specifically, it says that the probability of event A happening conditioned on event B is equal to the probability of event B happening conditioned on event A multiplied by P of A happening divided by P of B. I hope everybody is familiar with this, but we will talk about this a bit more in our future slides. We need these things called stochastic samplers. Stochastic samplers are basically the tools that we use to efficiently find the probability distributions that we actually want to measure. And combining all these things, we need some nice code. And this is where the parameter estimation package called Bilby comes in. And I'll talk about Bilby a bit at the end of my talk. And you can also, the day 3 tutorials also have Bilby in them, and you can basically play around with the various functionalities Bilby in there. Okay, so let's just understand the signal and the noise first. So the data that we observe in our detectors, D of T, has a lot of noise, and there's some signal embedded in that data. And I can write the D of T, let's say my data in the time domain, I can write it as a sum of a signal, which is also in the time domain, expressed in the time domain. This signal is contingent on a set of parameters theta. Now, this set of parameters theta could include the masses, the spins, the distance, the sky location, so on and so forth, and the noise. And when I add the signal and the noise together, that's when I get data. I could equivalently also take Fourier transforms of these time domain objects and get and express these quantities in the frequency domain or the Fourier domain. Okay, so let's just talk about the signal for a few moments. This gravitational wave signal has two polarization, exactly like light. And these two polarization are the so-called plus polarization of the gravitational wave and the cross polarization of the gravitational wave. And both these polarizations are described by 15 parameters in case of a binary black hole. These include intrinsic parameters, that is the masses and the spins. So the mass of the two black holes involved in the merger, the three-dimensional spin vectors or the angular momentum vectors of the black holes each, and also extrinsic parameters such as the distance, the sky location, and something called the polarization angle, etc. And given these two polarizations of my gravitational wave, I can write the total signal h of t given theta. Sorry, I just changed the notation slightly a bit here. I can write that as something that depends on the polarizations, which is again a function of the parameters themselves, and a factor which depends on the sky location and the polarization angle of the binary with respect to us. So, these factors are called the antenna pattern functions. Okay, so just let's discuss about how the signal really looks and what the effect of varying the parameters on the signal is. For instance, if you have a higher mass signal, if you take, let's say, a signal with mass 1010 and then you compare it with a signal of mass, let's say 2020 for the two black holes involved, a higher mass will always give a shorter signal, but it will give more amplitude at the same distance. For instance, you can see it here. When I increase the mass, when I go from low mass to high mass, the signal itself becomes shorter, but the amplitude of the signal, the strength of the signal actually increases. Okay, so this is the effect of varying mass on the morphology of the signal. We could also imagine, changing the spins. So I'll just pause the video for a second and talk about what is being done in this video. This vector is perpendicular to the plane of the rotation of the binary, and it is also the direction of the orbital angular momentum of the binary. And if the individual angular momentums of these black holes, we call them spins, if those spin vectors are actually aligned to the angular momentum, and in the positive sense, so they are aligned to the angular momentum or parallel to the angular momentum, that essentially increases the length of a waveform. If there's zero, so compared to the case when there is no spin at all. And if these two spin vectors are anti-aligned with the orbital angular momentum, that decreases the length of the waveform, as is shown here. The binary with the spins anti-aligned merge first, followed by the one with zero spins, and finally the one which has spins aligned to the orbital angular momentum merges the last. One very interesting thing that happens in binaries where the spin vector is no longer aligned with the orbital angular momentum is that the orbit starts precessing. And when that happens, there are these discernible amplitude variations that you can see in the waveform. And that's a very interesting feature of precessing systems. Both these visualizations were actually taken from this nice package called the Binary Black Hole Explorer. I would encourage you to download that and probably play around with that as well. Okay, let me go forward. Okay, so that's it for the signal. And we talk a bit about the noise now. Some of this has already been covered in Pekka's lectures yesterday. But just to repeat, the noise property is generally unknown and need to be calculated from the data. And given a data stretch, we have to calculate the noise properties. And contingent on the following assumptions, the assumption that the noise is stationary, that is, the noise properties do not really change with time, and the assumption that the noise is a colored Gaussian, which means that the noise properties are different at each frequency, but described by a Gaussian process at each frequency. We can describe the noise properties by the power spectral density, which is denoted by S subscript n of f in the frequency domain. So we can describe the properties of a noise by a power spectral density, which roughly looks like this. So this is data from around the event GW15 and 14, and this is what the power spectral density for that event, for the data around that event really looks like. Okay, so you can think of the PSD as being proportional to the variance of the noise at each frequency. When I say variance, I mean it in the sense of the Gaussian distribution. So there's a mean of the noise which is taken to be zero, and the variance of the noise is basically given by being proportional to the power spectral density. And what I can hence say is that the probability of getting a noise sample Ni at any frequency Fi is proportional to a Gaussian. This is something that looks like a Gaussian at least. So you have some Ni square in the numerator, and you have an the Sn of Fi in the denominator, which essentially also sort of tells you that the past spectral density is also looks like the variance of the noise. Okay, how do we estimate the PSD from data? One of the more famous methods is to use the Welch method. What this involves is dividing the time series data into small segments. They could be overlapping segments as well, and taking the Fourier transform of each segment calculating the Fourier transform of each segment and calculating the mod square of that quantity and averaging it over all segments. So naturally, if we have more data to average over, we'll have a more accurate estimation of our PSD, which is shown in the plot on the right. So if you just take a 64-second data and do the PSD, you'll get some noisy kind of curve. But if you take, let's say, 1,024-second data and do the PSD of that data, you'll get a more accurate estimate of your PSD. Okay. Right, so once we've learned about the signal and the noise, we jump on to talk about the Bayes theorem, which I briefly also mentioned in one of my earlier slides. So what I'm going to do is I'm going to take the Bayes theorem, which I have already mentioned, and change A to theta, send A to theta, and send B to D, which stands for data. Just by changing the notation, what I get is P of theta given D equal to P of D given theta multiplied by P of theta divided by P of D. Now notice that I will promote all of these to also a probability distribution. Here we were talking about individual probabilities, but now we will think of these P's as probability distributions, and we'll also give these probability distributions their own separate symbol. So we'll call the left-hand side the P of theta given D by the small p. This is called the posterior distribution of parameters. So, and we'll call this P of D given theta by the curly, the curly L, and this is L of D given theta. This P of theta goes to pi of theta, and we'll call the thing in the denominator by just the ZS, which is called the evidence. The pi of theta is called the prior, and the curly L is called the likelihood. We will talk about each of these in some detail in the next few slides, but understand that we want the problem of parameter estimation is to actually estimate the left-hand side of this equation. It's called the posterior distribution, the probability that a set of parameters theta describes the signal. Right. Okay, so let's go on and understand terms in this equation. The first thing is the likelihood. So we know that, so likelihood is basically the probability of D given theta. We know from the noise properties discussion that we just had earlier that at each frequency, the residual after subtracting the best fit signal from the data should look like noise. And hence it should follow a Gaussian distribution, right? Because the noise follows a Gaussian distribution at every frequency. Hence, the likelihood function distribution can be written as a Gaussian distribution in the residuals. That is, for each frequency, we can write the probability of getting Di given theta as proportional to some exponential of D minus H square. So what I essentially mean is if I take the data and subtract my signal from it, I should get noise. So this is basically just noise. And I square it and divide it by the past spectral density. This is just, I mean, in some sense, I've just sent Ni to Di minus H, but this allows us to formulate a likelihood function which will turn out to be extremely powerful, as we'll see in the next few slides. The total likelihood for across the frequencies, because our signals are generally broadband signals and do not really reside at just one frequency, the total likelihood can be written as just the product of likelihoods for all the frequencies. Okay, fine. Let's go to the prior. Now, the prior distribution encodes the prior knowledge or belief, our prior knowledge or belief in what the parameters of the system ought to be. So this is really a distribution that the analyzer, the data analyzer, will set based on their prior knowledge or belief of the system. But there are some examples that might aid you in setting the prior distribution. So for instance, we do not expect that any of the directions in the sky are more probable to produce gravitational wave events. So what the prior on the let's say the sky location will be uniform in the sky area. We also, let's say, do not a priori assume that we have a lot of information about the mass distribution of, let's say, binary black holes. We'll put the prior on the masses of the binary black holes to be uniform. There are other priors that come just because there's a physical limit on something. For instance, there's a physical limit, or at least thought to be a physical limit on the maximum spin of neutron stars, and that means that we should restrict our prior on the magnitude of the spin to be less than, say, 0.89, and so on. As I mentioned, and I reiterate, this is a choice that we make when we're doing an analysis, and of course we need to justify that choice, but it is choice that we can make while doing the analysis. Okay, so there was something in the denominator which I forgot to say, but was an overall sort of normalization constant of the right-hand side. And this number, Z, was called the evidence. The evidence is actually used to compare different hypotheses for the data, say different signal models and so on. One very simple example of where the evidence is used is in comparing signal and noise. So say we want to find out how significant is the fact that we have detected the signal. Oh, that's not detected. Let's say how significant is the fact that the data contains a signal as compared to the hypothesis that the data contains no signal and just contains noise. We calculate the evidence, formulate the evidence for the noise at just Zn, with just saying that we just write it as the likelihood without the h on the inside the exponential. So it's just the mod d of fi squared divided by Sn of fi. And this is the so-called noise evidence. And the base factor of signal versus noise is just the ratio of evidences. So the base factor is just Zs, which I defined in the earlier slide, divided by Zn. Now, if the base factor is, say, above a certain cutoff, say 3000, we say that there is evidence for the signal being present in the data. Okay, so I hope that's clear. So we now have all the cool tools to calculate the left-hand side. We discussed about the likelihood, we discussed about the prior, we discussed about the evidence. So we now have all tools to calculate the posterior. But then we run into a problem. As I said, theta is basically a set of 15 parameters. 15 parameters is a very high dimensional space. And if you wanted to calculate, let's say, the right-hand side over, let's say, a grid of parameters in theta, gridding the space would be extremely inefficient. This is because, as you can imagine, the cost of gridding each dimension and scales exponentially with the number of dimensions. For instance, if you want to use 10 grid points per dimension, but by dimension here I mean parameter. If you want to use 10 grid points per dimension and you have 15 dimensions, the total number of likelihood calculations, or let's say the right-hand side, needs to be evaluated for 10 raised to 15 points. And that is an extremely time-taking process. And that's extremely inefficient, and we cannot, it's not a practical problem at all for our purposes. So the solution is to use stochastic samplers. I had mentioned briefly about stochastic samplers earlier, and I'll give you a demo on the next slide. So the idea of stochastic samplers, I've taken an example of so-called Markov chain Monte Carlo samplers. The idea of this is to populate the prior space with a lot of random numbers in the start. So that is the initial condition, so to say. And for each random number so populated, we take steps towards the direction that will increase probability. And we do that in a random way with the probability that the step is accepted depending on what the change in the probability will be. And what essentially will happen after that is that when we, so the thing, extremely sorry for this. So we start off with numbers populated all throughout the prior space. And as we go ahead, what we see is that the all these points that were initially in the prior space converge to, let's say, one point in one point, which was, say, the parameters that we actually put into the data. There exist other sampling methods too, for instance, as nested sampling, which is used very, very frequently in LVK data analysis as well. And there are a host of other sampling techniques. Okay, so, I mean, dealing with the data, calculating the waveforms, calculating the likelihood, sampling on it, and so on, might sound like a lot of work. And that's why we have an open source package called Bilby, which comes to the rescue. So a few words about Bilby. Bilby is a very user-friendly open source parameter estimation library. It can work with existing LVK data, but you can also simulate data. You can take fake noise and inject a fake signal and test your data analysis pipelines on that signal as well. It supports native, by native I mean samplers which are inbuilt within Bilby, for instance, Bilby MCMC, and open source samplers like MC, Dynasty, Multinest, etc. These are just names of Python packages which actually implement these sampling algorithms. And the best part is that you can also use Bilby to do parameter estimation problems in data which is not GW data as well. So for introduction to Bilby, using both real and simulated data, please do check out the day 3 tutorials. Okay, so I'll spend my last few slides on understanding what the output from a parameter estimation run is. So basically, the output from a parameter estimation run is draws or samples from the posterior distribution of parameters. This can be thought of as, say, a spreadsheet. So basically, you have all your parameters. Say, I've just shown 5 parameters here. So for each of those parameters, you have n number of posterior samples, and you can read or process these files with any standard tools. There's typically released H5 files, so you can use HDF, H5py, or NumPy, Pandas, all these standard Python packages. And histograms from these samples will give you the measurement of the parameters corresponding. So histograms from samples of each parameter will give you the measurement of the parameters. So for instance, let's say I take mass1 and mass2, I add them together, I add the two values together and draw a histogram of the masses. What I'll end up getting is this. I've taken this from the GW 150914 event and the Bilby samples for the 150914 event. For instance, and this is to illustrate what what the measurement of parameters actually looks like. So this is your posterior distribution, marginalized over all the other parameters, but only for this total mass parameter, which is just M1 plus M2. So what you can essentially do is you can find a region in this posterior distribution whose area is 90% of the total area let's say, 90% of the total area in this distribution. And you can call that 90% credible interval. And that then translates to the measurement of your parameters. So you can quote numbers like, say, 71, with 71 plus 0.53, which is, say, the median value of this distribution, plus 3.32 minus 3.26. And this plus 3.32 and minus 3.26 actually correspond to this and this line or in this distribution. So, so this is for one-dimensional distributions, but generically our output is not a one-dimensional distribution. It is a highly correlated distribution. So one could also try to look at 2D histograms and draw a collection of 2D histograms. By 2D histograms, I mean plots like this. And these are in popular parlance called corner plots. And these are very useful to look at correlations between parameters. For instance, I can point you to the correlation plane of M1 and M2, as you can see here. And you can see that there's a negative correlation between M1, the measurement of M1 and M2. There's also another very nice package which is used by the LIGO-WIGO collaboration called PE summary. And this is a Python package for reading in data and producing and also processing the data. By data here, I mean the posterior samples, processing them and also producing some really, really nice plots like this one. Okay, so that's it from my side for today. I'll leave you with some Bilby, the links to the Bilby and B summary documentations. And this first paper is the methods paper for Bilby. And this Thrain and Talbot 2019 is a really nice review on whatever I spoke about. So feel free to get in touch with me. This is my email ID. And of course, you can also post your questions on ask@hickman.org. Thank you.